right, so we're coming into our last part of Unit 6, and this is what I call the oddball integration techniques. These are the things that kind of are what to do when you have rational functions. So because fractions are typically harder, these are integration techniques when these rational functions maybe don't work out to be quite as nice. So we're going to classify this as rational function integration techniques. Now, and the interesting thing here is we actually in AB Calc do not need to actually do every possible rational function integration technique. Some of them would be in Calc 2 or BC Calc. I'm going to show you the ones that are in your AP Test CED curriculum guide. And so we're going to work through it. Then we're going to start with some easy ones, going back to what we already know how to do. So the first one is fairly straightforward. If I have a constant over linear, so that's this first one right here. These are always very, very easy. So anything that has a constant over linear, it's nothing more than a straightforward U substitution. So starting with the easy ones, sorry, I have to sneeze. All right, we would let u equal 2x. So just come down here and work it. So my du equals 2dx. And it is perfectly fine if the constant here does not match the constant there. That just means you need a corrector. So we would add in our corrector. So this is going to become the integral. We need to add in a 2dx. So 1 over 2x minus 1, 2dx. And we correct for it on the outside with a 1/2. And so we make our u substitution. We have 1/2 the indefinite integral 1 over u du, which we can then integrate as ln absolute value of u. Don't forget your constant of integration. Part of the good thing about coming back to this is to remind you that indefinite integrals include a constant of integration. And then we finish the problem by substituting back in. Another change from our definite integrals in the last notes is that you have to add the constant and you have to go back to x at the end. And that gives us our final value. So pretty much easy peasy, constant over linear. Now let's take a look at this idea where I have a linear function over something else, okay? And the moral here is that really the first thing that you should always do, okay? Always check to see if you can do u substitution before you try any of the fancier things that's going to come later, because u substitution might be exactly what you need. So don't go for the complicated stuff until you try the u substitution. So I let u equal the x squared minus 5x, because that's the inside function. Du would be 2x minus 5 dx in the differential form. And so what I see here is that this is a straightforward u substitution. My du is exactly the top of the fraction in that. I can rewrite this as the integral of x squared minus 5x to the negative 3, and then put this 2x minus 5 dx over here, so that this entire thing that I've highlighted in green is going to become u to the negative 3 and then the du that's there. And then we can integrate as normal using our power rule. Add 1 to your power, divide by negative 2, so that's the same as multiplying by negative 1/2. Add your c, because it's an indefinite integral, and then finish it out by substituting it back in. U was x squared minus 5x to the negative 2 plus c, and you might prefer it written in the form where we go ahead and get rid of the negative exponents, 5x squared plus c, and that would be our general antiderivative. Okay. If I look down here at number 3 again, notice that in this one, it doesn't really seem to be any quote-unquote inside function, but when we look for an inside function, a lot of times, if we can make u equal the denominator, that is going to be our kind of preference as we're looking at it. So like in this one, how I know that this is probably going to be a u substitution, notice how the numerator is 1 degree less than my denominator. And in that kind of framework of a rational function that has the degree on the numerator 1 less than the degree of the denominator, I am going to try u substitution as my first choice. So I would let u equal r cubed minus 3r squared plus 1. I would take the derivative, 3r squared minus 6r. And I look at what's in the numerator, and remember this has a dr, and I'm trying to match what's here in this to what's up here. And I'm like, okay, they're close. And remember, you can be missing a constant. So I might come down here and pull the 3 out because there's no 3 up here with that one. R squared minus 2r dr. And so you can see that we're almost there. The only thing we're missing is this constant. So we simply need a corrector, and this would be perfectly fine. So you do want to check that. Anytime the denominator is the degree of the denominator is 1 more than the degree of the numerator, or the numerator is 1 less than the denominator, how do you want to look at that? Check to see if you're letting u equal to the denominator works. So try that first. So in this, we would add in our corrector here, and then we would go ahead and integrate. So it's 1/3 the definite integral, and it becomes 1 over u du. And that reason we kind of let the denominator equal 0 is because that's our known derivative of the log. So it becomes 1/3 natural log absolute value of u plus the c, and then change it back to be in terms of x, r cubed minus 3r squared plus 1, and then plus c, and we're done with that problem. Right? So those first 3 are kind of our straightforward ones. Now let's come down here to number 4. So taking a look at this one, it looks very similar initially to what we did in the previous example. I see that my denominator has a degree 1 more than my numerator. So since this is of a similar form, I'm going to try the u substitution. Like you said, the first thing you should always do is try the u substitution and see if it works. I'm going to put this up here. So u equals x squared plus 5. My du equals 2x dx. Now, here's where we run into some problems. And so we first notice that our numerator has a whole bunch of extra things that are unnecessary. The constant in front of the x is not what bothers me. It's the fact that it's got this minus 1, and yet my du that I found does not have the plus 1 or minus 1 that's added in there. So no matter what I do, I'm missing a constant in the derivative of u. But this actually does not bother me. You have to remember that you can split fractions up. So my hint here says, let's split the fraction up. All right, I'm going to look at the rest of the stuff in a second. I'm just going to bring this down here. And so this integral from 4x minus 1 over x squared plus 5 dx, I try u substitution. I see that it's not quite working. I go ahead and I split my integral. So it becomes 4x over x squared plus 5 dx minus the integral of 1 over x squared plus 5 dx. And by splitting it up that way, now we can see that here in the first term, that u substitution that I was doing up there, this right here is very, very close to what I need. It just has an extra wider constant that's there. So we can pretty much kind of go through this, and I can pull a 2 out. But I don't really need a corrector. I just need to pull a rider out. And then I have my 1 over x squared plus 5, and then my 2x dx. And I'm going to just leave the minus for a second. I'll come back in and do the second portion of this in a second. But continuing with this, I could do my substitution, 1 over u du, and get to the 2 natural log absolute value. And I'm going to go ahead and put the u back in, x squared plus 5 here. And I like to kind of just do plus c at the end because we know that we don't need to put a plus c every time. We just need to do it at the very end. So we kind of have that going in, and by breaking it up, that allows me to see that I can use the u substitution on the first term. All right, now let's go look at the second term, which I've kind of left off here for the moment. So in that, we have a constant over x squared plus 5. Now, I'm going to remind you about the inverse trig rules. And so if you'll remember from our discussion on the inverse trig, let's do this in turquoise. So that the antiderivative of something of the form 1 over x squared plus a number squared is nothing more than the inverse tangent, and that we were going to memorize the special form here, which the nice thing is if you're in 2020 when we have open note, that's something we can certainly have on an index card over on the side, that this is of the form that we're looking at for that inverse tangent. So when I'm doing this problem, what I'm going to do is I'm going to do let's identify what my x and my a, well, we know what x is, but what an a is. So since we have a 5 in this location right here, and that's a squared, so a squared is equal to 5, a is going to be square root of 5. And you always use the positive value for a. So pretty much when we come down here and we're doing this problem, this simply becomes 1 over square root of 5, the 1 over a, inverse tangent of x over square root of 5 plus your c. And then from there, just in terms of linkage, I just need to keep bringing it down each time to fill in until I get to the final answer that we had here. So all I'm doing is filling it in, and notice that I already had the plus c there. And so the idea here is that first do your substitution, check to see if it works, and then you can split the fraction. If you don't have the correct du, you have an extra constant like that. All right, so what I hope you get out of this discussion, and again, we're just kind of doing all the different types of rational functions you might see, that if you have anything that is linear over x squared plus a number, that you can always split it up, use a u sub on the first one, use an inverse tangent on the second one, and you will be fine. So keeping that in mind, in the last little bit of just this set of notes, let's remind ourselves of the inverse trig integration forms. And look at the 3 that I have. Let's look down here at number 5. Okay, I'm not going to work these completely, but I'm just going to show you what I'm looking at. If you see something like the first one, when you have a constant over square root of a squared minus u squared, that's going to be an inverse sine function each time. So I would just identify that my a is 2, and that my u in this case is x, because sometimes that might be like 9x squared there. So we do want to look at that. But since it's an x, we can go straight to the arc sine or inverse sine of x over 2 plus c, and we're done with that problem. But look at the difference over here in b. Notice it's not a constant over that a squared minus square root of a squared minus u squared. It's got an x on it. And so in that, whenever I see that type of thing, this is not inverse trig. You're going to use a u sub on this problem. Anytime that you have it could be any constant times x, but basically we're looking at a linear term over the square root of a squared minus u squared. That is going to be a u sub, but it's going to be a u sub where you let u equal this 4 minus x squared. And if I do that, my du would be negative 2x dx. We would need a corrector, so negative 2, negative 1/2, and then we would kind of work through that problem. All right, I'm going to pause it and let you take a look at that and finish that out and then come back and check. All right, now in the last one on this is a very similar problem. Notice that it is also linear over that form, but in this one what you want to recognize is that what you need to do is split it. So rewrite it as x over square root of 4 minus x squared dx, and then do plus the integral of 2 over square root of 4 minus x squared dx. And then you would use a u sub here, and use inverse sign here. All right.